Sure. So we have the pleasure to have Leonid Ryvkin with us today from ICG Lyon and the University of Göttingen. Leo is going to introduce us gently to singular foliations. So please, Leo, entertain us.
Thank you very much, and thank you very much for inviting me to speak. It's a big pleasure. So I will try to be gentle. Please don't hesitate to slow me down if I'm going too fast, or vice versa. If I'm being too slow, you can certainly accelerate. The plan is relatively simple. So part one will be trying to motivate and introduce the notion of singular foliations coming from regular foliations. So from regular to singular foliations. And in part two, once we have established our objects, I will try to tell a few basic things about the first invariants one can cook up or local normal forms. So one has an image of how they more or less look and behave. Okay, so first of all, let us define regular foliations, and we'll do that in two ways, and only one of them is appropriate to be transferred to the to the singular world. So definition of a geometric regular foliation. Um, it's a decomposition of a smooth manifold M into immersed submanifolds. And this is not quite enough. So we decompose M as a disjoint union of some submanifolds. We call those leaves. And now the additional condition is that we have some control over how those manifolds lie next to each other. So we want additionally such that the decomposition is locally diffeomorphic to Rn. Oh, to Rn being decomposed as a layering of Rk's and the parameter space of the leaves is then exactly the codimension. Okay, so we say that locally we want a foliation to look like this. However, we have no control over how it looks globally. For instance, we could be on a torus and we look at curves which go at an irrational angle, so we have kind of dense leaves going around it infinitely many times. But if we zoom in sufficiently close into a small region of it, then we have parallel lines, and somehow from this local model point of view, we don't know that one leaf might at some point come back. Locally, we still have this image with the horizontal lines. This additional condition of the local triviality, it's not automatic. So I'll paint the standard example of a decomposition into immersed submanifolds, which is not a foliation. So this was a foliation. And non-foliation is if we take R2 and we take one vertical line as an immersed submanifold, and then we take the half lines horizontally to both sides of it. So near the red line, there is no way to straighten the vertical and the horizontal lines into the model case. So this would not be a foliation for us. I will send around a document with a nicer picture of a more geometric example of it, where one takes somehow a circle in R3 and one interprets it as something through which a current goes, and then one would have somehow the field going through it, and the circles all arranged nicely, but the red circle is somehow conceptually a different thing and doesn't lie neatly next to them. Okay, so this was the geometric definition. The algebraic definition of a singular foliation, so regular foliation for now, sorry. So algebraic or infinitesimal is maybe the better word. So it's a subbundle F for foliation in Tm, such that if we take the Lie bracket of a section of it and another section of it, the result lies against inside it. And this is usually called involutivity. Okay, so those two definitions are equivalent by what's called the Frobenius theorem. There are some lines appearing over the screen. I'm not sure. Is it me or is somebody accidentally creating them? So the Frobenius theorem will not prove it, but we maybe should say how the correspondence worked. So to get from the geometric decomposition into the infinitesimal one, we just take the tangent spaces of the leaves and their disjoint union. And this will be uh, a priori just some set in Tm, but because of the local triviality, it's actually a subbundle and even an involutive one. Starting from F, in order to get the geometric foliation, we have to follow flows of vector fields in F. Um, so let's say we want to say what is the leaf through some point P. P is a point in the manifold. And we just say it's phi x1 of P, where x um, is a vector field in the foliation. For things to work properly, one has two choices. I will allow time-dependent vector fields. So x is actually a map from, I don't know, r times times m to f, not just from m to f.
And why do you need this time dependence?
So it is possible that one can always avoid it. In the singular case, I'm more sure that that one cannot avoid it. I think what people usually do instead is they don't take time-dependent vector fields, but a finite sequence of vector fields. I think it might still be true without the time dependence, but showing that this is actually an equivalence relation, so that it kind of not an, yeah, that somehow if you can get from A to B with a flow and then from B to C, for this it's easier if you allow time-dependent flows or concatenations of finitely many. But I'm not aware of a direct example where we wouldn't be able to reach. Probably you can avoid it. So I'll put this in brackets. Mm, but I'll still write down the second characterization that alternatively we can do somehow time one flow at x1, time one flow at x2, and so on up until xk of P. And now they are ordinary vector field. Mm. I'm still thinking, so I think I know the problem about reaching everything in slightly different contexts. I think in the a symplectic context, usually when one works with Hamiltonian diffeomorphisms, one really needs multiple ones, but I would have to check if the example they have there, why it shouldn't work, also creates an obstruction here. I'm really not sure. Okay, so we have two different ways to describe the same thing, regular foliations. Uh, mm, I will give a few classes of examples. So The first class is fibers of a submersion. So we have a submersion between manifolds. We take the fibers as leaves, and more or less the rank theorem or the implicit function theorem will tell us that those form a foliation. Then we could look at the horizontal vectors for a flat connection. On a vector bundle. And a third class of examples is, for example, the orbits of a constant rank connected Lie group action. And so the choice of examples is partially because all three can be very economically illustrated by the same picture of a Möbius band. So I can see it as a vector bundle over a circle. Then one foliation I could look at is the foliation by fibers.
In this last example, by constant rank, you mean the constant rank of the fundamental distribution, yeah?
Yes.
No, all right.
Yes. So constant rank of the space generated by fundamental vector fields. On the Möbius band, we have one foliation which is just the foliation by fibers. We can have the other foliation, which I will not attempt to draw into the same picture. I'll just redraw the Möbius band now as a rectangle and assume the opposites glued together, and then the horizontal lines would be the other foliation, which corresponds to a flat connection. Or one can realize both of them, or no, one can realize the second as an action of S1 on the Möbius band. Or R, just by picking a horizontal vector field. Okay, so especially in this third example, we have made a very, very strong admission. So we requiring the fundamental vector fields to span a constant rank distribution. This is very strict. Most actions we look at in everyday life wouldn't do that. And one of the possible motivations to go to singular foliations instead of regular ones is allowing any orbit of an action of a connected Lie group, any action of a Lie algebroid even, etc. Okay, I'm now attempting to switch pages. Okay. Do you see the page 2 now?
Yes. I suppose since everything vanished, it means that we are on page 2.
Yes. Okay. So I will now write down multiple possible ways to reformulate this infinitesimal perspective on regular foliation. So we have said that it's somehow F is a subset of Tm, which is involutive. But we can look at basically different formulations of the same thing, which then in the singular world will become very different. So one thing we could look at is we could look at the sheaf gamma f. Gamma f of sections of f. This is, in some sense, a very natural perspective because both when we try to define leaves as flows of vector fields in F, we actually just use the vector fields. We don't really use the individual tangent spaces very much. When we phrase what is involutivity, we actually use vector fields. So formulating it in terms of a sheaf of sections is in some sense very natural. So it is a sheaf of C infinity M modules, meaning that we can multiply a section on some open subset with smooth functions on this subset. So when we talk about flows, sometimes we want to know that they exist. And in this context, it might be useful to talk about the co-sheaf of compactly supported sections. So it's basically to any open subsets in the manifold, we associate the vector fields tangent to F with compact supports. And it's for us, it will be just a technical distinction, but strictly speaking, it's a different type of object. Now comes something which is somehow possible just because we're in smooth differential geometry. If we take gamma of f, so the global sections, they know everything about the local section. This is a particularity of smooth manifolds. We have a partition of unity. So if we know what it means locally to be inside F, what it means globally to be inside F, we know what it means locally. And this means that we can forget all the sheaf business and just look at gamma F. And what is gamma F as an object? Okay, it's the sections of a vector bundle. It's module over C infinity of M. We don't just know how to add things or multiply with scalars, we can multiply with smooth functions. So module gamma f, or we could look at the C infinity M module gamma CF, the compactly supported version of it. We can look at both of them also as modules just over compactly supported functions, but maybe we don't want to really go there. But we have kind of various ways which are in the smooth setting all equivalent. And then one thing which we could also do is we could look at what differential forms annihilate F. So we could look at gamma of.
What is the meaning of a cosheaf? I know what
Sorry,
is sheaf. What is cosheaf?
a cosheaf.
What is the
Um,
cosheaf?
So a cosheaf, so formally speaking, a cosheaf is the dual definition of a sheaf. So you have somehow, I don't know, would you prefer a formulation with functors or rather by hand?
Like I could understand. That's funny. Because
So basically,
of any sections of a certain bundle or not?
So sheaves are, if you think of sheaves as sections of a bundle, you can think of co-sheaves as compactly supported sections of this bundle. The idea is that while on I don't know, if you have U inside V, then you have a map from gamma V to gamma U, which is the restriction, and sheaf axioms are built around this. But you have also a map from gamma CU to gamma C of V. You extend a section by 0. And the co-sheaf axioms, are built around the extensions. So instead of a sort of gluing axiom, you have a co-gluing axiom, which is a little bit weird, but it's somehow a formal dualization of the concept. And so for my personal taste, the biggest relevance of co-sheaves is that if you take their duals, you get sheaves. So for example, if you want to define what is the sheaf of distributions on a manifold, the most convenient way is to look at the co-sheaf of compactly supported functions or sections and dualize it. Um, uh, did I answer the question? Sorry, I don't see
No, very
here.
much.
So I
Sorry?
think we can.
You build locally. There is no problem of extensions of anything. What I don't find here any sense of this procedure. Sheaf is something which informs about very local properties. Sheaf of a function, sheaf of a section, and so on. What is behind a certain neighborhood doesn't matter. So here is it true that if you have just a subboundary, F is a subboundary, and we have sheaf of sections, is it true that the co-sheaf is a sheaf of sections of the annihilator? So it's something in the dual boundary. No?
Sorry, so I'm not sure if I fully get. So basically, one could say that in this. This is just somehow a different formal framework to, in our context, describe exactly the same space. We don't need co-sheaves, and we will not need them later. Some people prefer to work with them, and there are some contexts in which they are a useful notion. Here, it's really just 4 or 5 different ways to see exactly the same thing. And if you want flows to exist, you might feel tempted to work with compactly supported sections, or if you want somehow the more I don't know, delocalized version, the corresponding co-sheaf. But here it doesn't really matter. Like all of those are exactly the same informations. There are in principle settings where it really matters to have a co-sheaf. Here it really doesn't. So there are theorems which are more or less telling us we don't need to care about co-sheafs if we don't want to. So so what you said is exactly right. We are only interested in the local information, and because C infinity M is a fine sheaf, we can always extend. We can always glue things. Then we can look at the whole module. We can look at the compactly supported ones. We can look at germs. It all doesn't matter. It all carries the same information. So
No, I think we can continue.
Okay.
okay. So now we come to somehow a distinction which is not only a matter of taste, but which will in the singular world actually change something. And that is, if we, instead of looking at sections of F, look at sections of the annihilator of F. certain subspace of one forms on M.
I'm sorry, I don't know what happened. Yeah, I'm very sorry. I don't know what happened with our installation here, but I had to switch from the very sophisticated system to just a computer, but we can continue.
Okay, just let me know if I should stop. So we had 4 essentially equivalent formulations, and now one which will later be actually different. It's when we look instead of sections of F, sections of its annihilator in the cotangent bundle, which is a certain set of one forms. Then the involutivities can be rephrased that the exterior differential of this space is in the ideal generated by it. So in the equation, something like this. And if we would generalize this notion to the singular case, we would get something which I think people call co-foliations. And if we generalize any of the 4 or 5 of the top ones, we will get a notion which is foliations. And in the regular world, they are exactly the same thing. But in the singular world, they become different. And we are going to focus on the foliation version, so where we generalize the sections of F and not the section of its annihilator.
Excuse me,
Yes.
what is the smoothness of your generalized distribution?
I haven't defined it yet. We were in the regular world
Okay.
until now. But yes, so this is where we are going. I thought before going to the singular world, I would translate the regular world into algebra, or more precisely, quote a few theorems which allow us to do that. So, intermezzo on translating geometry to algebra. So there are 2 things. The first one is maybe the fact that if we look at the smooth manifold M, and we just look at its smooth functions as an algebra, we can fully reconstruct M from it. So C infinity M knows everything about M. If you want to formalize it, it would be the statement that, for example, that the functor from manifolds to commutative algebras over R, let's say, sending M to C infinity M is fully faithful. But without categorical language, it basically means that given an algebra which comes from a smooth manifold, we can reconstruct the smooth manifold. Given a map between those algebras, we can reconstruct the map between smooth manifolds it's coming from. And I'll just kind of hint at where the information about M is hidden in C infinity M. So the points of M, we can find them as algebra maps from C infinity M to R. So we take a function and evaluate it at f of p, and this is the only way how we can get a map from the algebra C infinity M to R. Well, non-zero, yeah, unital maps, so mapping 1-to-1. We usually when one translates somehow, when one does algebraic geometry and one translates a space into its algebras of functions, one would like to think of points in the space as being ideals in the algebra. So this can also be seen as maximal ideals M in C infinity M. But it's not all maximal ideals in general, it's just those where the quotient is R. So with C infinity M mod M, this will always be a field, but it could be a different field in general, and we want this field to be R. For compact manifolds, this second line is not necessary. There, all maximal ideals are given by points. In a general non-compact manifold, we have additional maximal ideals, which are a little bit messy, and we don't want to talk about them. So we get points back as those with residue field R. Okay, so the first thing was translating a manifold. The second one will be about translating vector bundles. So when we have a vector bundle E over M, and we look at it instead as sections gamma E as a C infinity M module, so this is also fully faithful. So we can reconstruct the vector bundle essentially from the information of its sections. So fully faithful. And if we want, for example, to get the fiber of the vector bundle back from gamma E, we can basically look, for example, so EP could be reconstructed as we take gamma E and we divide it by the maximum ideal of the point P times gamma E. And that gives us back the fiber, etc. And this map, it's not just fully faithful, but if we just look at projective modules at the right-hand side, then it's also essentially surjective. So which means that any projective module actually comes up to an isomorphism from a vector bundle. So maybe a remark, definition, P projective if P plus Q is a free module. So if it's isomorphic to the algebra we are talking about, which in our case is smooth functions, to some power.
So probably finitely generated, yeah.
So for me, the definition of projective includes that it's finitely generated, because otherwise, so yeah, if you want to allow infinity in place of the n here, then I would add finitely generated. Okay, so there is one exercise which I tried to do in preparation of the talk. I will probably not write down the details because they turned out longer than I thought, but just as an example, we can look at the smooth functions on S1 So let's say that's our algebra. We can now look at the following module. So we fix some point in this one sphere, and we look at the functions on S1 that vanish at this one point that we fixed. So this it is the same thing as the maximal ideal of the point P that we have discussed before, but it's also a module, and one can show with a slightly longer calculation that MP is a projective module. So this means that there exists a vector bundle over S1 such that the sections of E correspond to MP. And one can show that this vector bundle cannot be trivial, and it is a rank 1 bundle. So this will be, again, the Möbius band. This might reappear at the very end if we get to the examples. Okay. Do I understand correctly that we do a 15 minutes break relatively soon?
Yeah, as you please. Sort of, you are to point the moment when we take a break. Yeah, but roughly speaking, yeah, within 5 minutes, say, or so. Yeah.
Okay, then maybe I would actually define singular foliations, and then the break could be somehow space for the definition to sink in. Okay, so definition. Singular foliation on M is a C infinity M subsheaf of vector fields on M, which is of finite type, which means that it's locally finitely generated. And involutive. So basically, we are now taking the perspective of irregular foliations was a certain subset of the vector fields, and now we just weaken the condition. It doesn't need to be locally free anymore. It doesn't need to come from a vector bundle. It just needs to have finitely many generators locally, and we still want it to be involutive.
So one natural question, because there is no theory of singular foliation done by Sussman, etc. So do you refer somehow to their concept?
Yes. So I will write down the equivalent definitions, and then I will relate it to their notion. So if you don't like sheaves, you can also say that is a C infinity of M a submodule of just the vector fields on the manifold, which is, and then has the same two properties. So basically, again, because we have partitions of unity, global information, the global sections of the sheaf know everything. And you can play around and find other equivalent formulations. So the first one is the one which carries over most nicely to complex geometry, so to analytical foliations. The second one is the one used by Androulidakis and Skandalis, originally in their papers on holonomy groupoids and their NC star algebras of singular foliations. So if I remember correctly, this is somehow very close to this Stefan Sussman foliation approach. To my memory, they don't fix the module, but just the singular distribution. Is this correct, Janos?
Yes, yeah.
Yes.
They start
So
with distribution. So
yes,
they consider foliation as in the standard case as obtained from integrable submanifolds for this distribution. And there is a natural condition. So involutivity is not enough in the smooth case. So there is a stronger condition, yeah, so that this distribution should be preserved by flows of vector fields belonging to this distribution. So involutivity is generally too weak assumption.
so this is exactly the same here too. So after the break, we will see why we need the locally finitely generated condition, because otherwise we can construct examples where a resulting object is very badly behaved. And so these foliations, they induce foliations in the sense of Stefan Sussman. However, the sheaf knows more than just the distributions. We can somehow remember vanishing orders at points, etc. And it is an open problem whether any Stefan Sussman one is induced by a singular foliation in this sense.
Yeah, if I remember well, there is a theorem that locally finitely generation for the Stefan Sussman implies their condition of integrability.
Yes, exactly. So it is, strictly speaking, a stronger condition.
Yeah,
However,
this is stronger, yeah. So.
yes,
But it is automatically satisfied, for instance, for leaves of symplectic leaves of Poisson, tensor, etc., because these are automatically finitely generated. Yeah.
yes. So it is an open problem whether there exists a Stefan Sussman foliation which is not which cannot be generated by, let's say, Androulidakis Skandalis foliation.
Okay.
So
Okay.
everything coming from things like Lie algebroids, Dirac structures, and so on,
Yeah.
those will all be foliations in our
Yeah.
view.
Maybe.
And yeah,
Just, just, yeah, just a comment. The starting point for Stefan Sussman is not a distribution; it's a collection of vector fields that act on a manifold, and we consider the Lie algebra, which can be of finite or infinite dimension, doesn't matter, and we are asking whether orbits form a foliation. So the distribution is actually the second step. They just start from a collection of vector fields.
mhm. Yeah. So in that case, it is somehow more the definitions start coinciding. Once you say basically we consider two collections equivalent if they span the same space inside the vector fields. Good.
Yeah, well, what I want to say is that I mean, you don't start with a distribution. I mean, with a subbundle, you start a collection of a vector field. But when you look at the orbit, you have to add Lie brackets, so you have to close the Lie algebra generated by those vector fields, which need not be finite dimensional. So it need not be even a pseudo Lie group. It can be a Lie group of infinite dimension. Say Lie pseudo group of infinite dimension.
Okay, so we are probably ready to take a break. I propose that we resume at 3:15.
And I'll maybe send in the Zoom chat the written notes that I have for the talk, because there are pictures which are slightly better painted than what I could do by hand.
Yes, please do.
And we can continue.
Okay, so in the break, I just wrote down two key distinctions I would like to make. So one of them is that somehow the idea behind the singular foliation, how Androulidakis Skandalis looked at them, is that they want to actually remember to a certain extent the vector fields. So basically, the way how we define singular foliations is as a module, meaning that for us, vector fields vanishing at the origin of R2 and vector fields vanishing quadratically in the origin of R2 are different things, even though both of them, if we look at the tangent spaces, at the origin the tangent space is 0 and elsewhere the tangent space will be everything. If we look somehow, if we take our vector fields and we evaluate all of them at all points, we get the subspace of the tangent bundle, and it will be the same for both, but for us, they will be distinct objects. So,
But this is not only the question of distribution. If you think in terms of leaves, so both foliation have the same leaves.
yes.
So the definition seems not to be geometric in the sense that there is no geometry which distinguish these two foliation, which consist of two leaves. One is one point and the other is the rest. So yeah,
That's absolutely true.
yeah, so this is algebra, not geometry.
It is algebra, but I think that to a certain extent it is also dynamics. So if you have two different Lie group actions, they could have the same orbits, but they could be very different actions. And now it's a matter of taste. Do you want to remember do you want to remember only the orbits, or do you want to also remember the dynamics? So somehow this foliation is also the same thing as the action of GL2 on R2. And of course, we could also look at the action of, I don't know, of C star on R2, different Lie algebra or Lie group action. Maybe I'll write the Lie groups here. Um, Having the same leaves, but one could, but they are different actions, and in certain contexts, it makes sense to distinguish them. So I think that for Androulidakis and Skandalis, they are actually interested in the dynamics because they use the vector fields in the foliation to talk about differential operators. So for them, this distinction is actually relevant. If you're working with a Poisson structure, arguably you would also be interested in this distinction, but you're right that there are contexts where they might not, this distinction might not play a role, and then somehow geometry would only be the shadow of this sheaf or of this module. The tangent spaces would be enough.
No, but in this case, the geometry is the action, not the foliation.
Yes. Yes. So yes, this notion of foliation is not purely geometric, if you want. Okay, there is so there are multiple types of things one could look at in this context. One of them is examples. So all examples, almost all examples we know of fall into the following class. let A rho to Tm M be a Lie algebroid. If we then use the anchor of the Lie algebroid to generate us something in the vector fields, this will be a singular foliation. I don't know if everybody is familiar and comfortable with Lie algebroids. They will start playing a role a little later, so maybe I say the definition. So a Lie algebroid is a vector bundle with a linear map into the tangent bundle, fiber-wise linear. And we want gamma of A to have a Lie bracket which is compatible with the anchor and which derives functions. So gamma A has bracket such that xfy is the same thing as fxy plus x rho of x applied to fy. And those things can be constructed from, for example, Lie group actions. So I'll write it directly infinitesimally. So if G to xm is a Lie algebra action, then we can see it as a Lie algebroid just as the trivial bundle m times G. And this map induces us an anchor map and also a bracket. If we have a Poisson tensor, so a bivector field with certain properties, then T star M becomes a Lie algebroid with the anchor given by pi dash. It turns a covector into a vector. If we have a regular foliation, then the inclusion turns it into a Lie algebroid, and the bracket is the one we had before. Okay, so basically, we will not need a lot of Lie algebroids, but infinitesimal action, Poisson structures, regular foliations, all can be seen like that. There is the following open problem. Does the foliation given by vector fields vanishing quadratically in the origin of R2 come from a Lie algebroid? So the answer to this is unknown. I think it is proven that it cannot come from a 6-dimensional one, but maybe the argument also works to say it's not a 7-dimensional one, but we don't know if there might be an 8-dimensional one generating it. Maybe I'll write down why the number 6 turns up. The generators of the vector fields are x squared dx, xy dx, y squared dx, and the same things with dy. So somehow writing down those generators tells us that this is certainly finitely generated. And now for involutivity, we would pairwise check the brackets and see that if we bracket two things of degree 2, the result will have vanishing degree 3. So it will be something like x squared times y, which we can describe as multiples of those 6 again. Much more widely, it is not known if there are foliations which don't come from Lie algebroids. There is one counterexample which was constructed by Androulidakis and Zambon, which basically uses a foliation which is locally finitely generated, but globally needs infinitely many generators. You just kind of go into infinity with higher and higher degrees. So this cannot come from a Lie algebroid more or less by definition, but it's not known if there is any example which works on a compact manifold or locally. And even for this one, we don't know. So if you have some free time, Anju, please figure it out and tell me. I'm trying to understand what's going on there for a while and couldn't find an argument yet. Okay, so now we have defined something, and as Janusz said, for now it's not geometric. For now, we don't even know whether it induces something geometric. So we would like to have a theorem of the sort a foliation has leaves, and then we should also say what leaves are. So we can give two definitions of leaves. So one of them is dynamical. And it is the definition that I wrote down earlier. So for the regular foliation, so the leaf through a point P is everything I can leave if I apply flows of vector fields in the foliation to P. And the other one is somehow purely infinitesimal or geometrical. It is submanifolds such that their tangent spaces are exactly the directions of the foliation. So such that T at any point of the leaf is the same thing as if I evaluate at the point Q all the vector fields of the foliation. And this is somehow non-unique, so one could ask for them to be maximal. So theorem, those are the same. I think this theorem is originally due to Stefan Sussman, Hermann, but also many people have been proving similar theorems of this sort independently from one another at a similar time. And those basically tell us, okay, before we had somehow an equivalence between dynamical information and geometrical, now we can at least recover the geometry from the dynamics. And if we would like to give a geometric definition of singular foliations, then somehow all the definitions we discussed earlier, so the one from Stefan Sussman and so on, they somehow all, at least at some point of the construction or at some property, go through the dynamical information through the vector fields. And one of the reasons why it might be convenient to do so is that for singular foliations, there is no one unique normal form. So if I just look at R2 as a singular and put a singular foliation on it, with the origin as a singularity, the orbits could look completely different. So they can spiral. They could be parallel lines interrupting at some point. There could even be just a row of singularities in a line, etc. So all of these pictures we can generate just as flows of one vector field. A flow of a vector field, the flow lines will always form a singular foliation, or the module spanned by the vector field will. So we don't really have a unique local model, which means that we cannot really mimic the definition of regular foliations using a local model here. Okay, so in the definition, we had two conditions. One of them was involutivity. The other one was being locally finitely generated. I will try to give an example, or just to state why we need both of them. So I'll start with the easier one. So what happens if we have no involutivity? Then I could, for example, look in R3 at the vector fields dx and dy plus x dz. This is somehow the standard contact structure, the contact fields of the standard contact structure. Those two vector fields, in every point, they span a two-dimensional distribution. It is not involutive. If we take Lie brackets of those, we can reach the whole space. And if we would follow flows of those two vector fields, we would also be able to reach the whole space. So here, a dynamical leaf, there is only one, is the whole of R3, and somehow the geometric leaves don't really exist. And the second example I wanted to give is what happens if we have no finite generation.
I'm sorry, they do exist, but are one-dimensional.
Oh, okay. So then you're using a different definition, because here I required for the tangent direction to be equal. If we would require them just to be subsets, then you're right that they would be one-dimensional. Okay, so now I'll write down. I want the foliation to be generated by vector fields in R2, and in general, such a vector field has two coefficient functions. And I now say that f is arbitrary, and g is 0 if x is less or equal to 0. So if I would want to do it as a picture, I would have horizontal lines allowed everywhere, but vertical lines would only appear on the right-hand side. So this is somehow the allowed directions to walk in when following flows. So one can check, this is indeed involutive. However, the geometric leaves and the dynamical leaves are not the same, because what we get is a dynamical leaf. Oh. Is everything is one leaf, because we can, if we want to move from here to here, we just move to the right, change height appropriately, and move back. So using 3 flows, we can move between those two. So this would also be a case where we use a concatenation of multiple vector fields. But the geometric leaves, they have to be one-dimensional on the left-hand side. So there, it is not possible that everything is just one leaf. And on the right-hand side, they have to be two-dimensional, so somehow the linking vertical line cannot be either of the two, so geometric leaves, not really well behaved.
May I make a comment, please?
Yeah, of course, please.
For the second example, the dynamical leaf exists, and it's the whole R2, but you have to define this action not by flows at 1, but flows at any times, positive and negative. In other words, you consider the action of the group of local diffeomorphisms, local flows if you want, and then it's always a submanifold. That's a theorem of Sussman as well. So there
Yes.
exists a geometric leaf if you allow going backward and forward in time along your vector field.
Yeah, sorry. So I think what you're saying is that the dynamic, what I call dynamical leaf, because so geometrical leaves for me are really, it's a very restrictive notion. Maybe I should have called them somewhere a little bit differently too. But it's submanifolds whose tangent space at the point coincides with the plane spanned by the vector fields. So this is why somehow I wouldn't call it a geometrical leaf, even though it is. I mean, it's this theorem of yeah, it's Sussman and Nagano, I think, which says that basically any family of vector fields, if you allow concatenations of flow, gives you leaves which, in some sense, foliate the manifold.
Which are submanifolds.
Yes.
So in other words, the orbit of that action are submanifolds, but you have to define at least a local action. That means you wrote flows at one, while you should take flows at any t positive and negative.
Mm-hmm. Yeah, so you're talking about the distinction between the attainable sets and the orbits, about the flows. Yes. And kind of, if you allow multiple flows, so the way we wrote it here, we have multiple flows, then everything is fine because in accordance to our definition, if x is in the foliation minus x is 2 and any rescaling of x is, so we can kind of avoid this allowing different times by just allowing concatenations of flows.
Right.
No, but this should be a module, so minus vector fields is also in the family.
Yeah, this is exactly what I'm saying, that we look only at very particular families. So for us, minus and rescaling are automatically in it, so we don't need to somehow ask for it separately. Absolutely correct. Okay, so one last non-example, and it's the fact that it's the fact that our foliations, singular leaves are always lower dimensional leaves. So basically, this is what for singular distributions people denote as being smooth. It's the idea that if I have a vector tangent to a foliation, I must always be able to extend it to a vector field tangent to the foliation. And this means that, for example, something where I have, I don't know, let's say one-dimensional leaves, and the rest are all points, this is not allowed. So this picture cannot come from a foliation. I think Camille always says that for our notion of foliation, you can lose a single spaghetto in a lasagna dish, but you cannot lose a lasagna leaf in a spaghetti dish.
You can if you take this dual approach, differential forms pointwise, but not in the smooth category. That means you dualize pointwise.
Yes. So this would be there are different notions which can accommodate that. Yes. Okay. Last remark, somehow coming from the this is somewhat a little bit, I don't know. I don't want to say embarrassing, but it's a weakness of the theory, in my opinion, and it's the fact that there is no general easy notion of morphisms between singular foliations. So morphisms are subtle. There is a class of maps for which we know what morphisms are, and it's, for example, surjective submersion, or a little bit more generally transverse maps. But in full generality, there are multiple competing notions. The equivalences are not fully clear. And usually a morphism between singular foliations in those more complicated settings is not just a map of the underlying manifolds preserving something. So one needs to add some structure, which one doesn't always want to do. So, but okay for submersions. Maybe to show where the subtlety is in general, I will say what happens for submersions. So imagine we have a singular foliation MF, and we have a singular foliation M prime F prime. And I want to say that phi is a morphism of singular foliations between them. So what I would like to do is I'll just take the inverse image of F prime and ask F to be in it. And the problem is a little bit with what does it exactly mean? Because we don't really have a map from xm to xm prime. This because when we look at the diagram, the arrows just don't match in the right direction. This is something which would be easier if we were in the dual picture. So basically what we usually denote by this, and I'll use an exclamation mark because it's somehow not fully just a pre-image, it's something of the following sort. We start with a vector field on M prime. We can turn it into a section of the pullback bundle. So it's phi star of Tm prime, it's not Tm, as a bundle over M. Now we can say that this is something where we can look at the pre-image of T phi. So T phi is something which takes a vector field on M. We just fiberwise apply T phi and we get something in here. And so basically our way to get phi exclamation mark of F prime is we start with the F here, we move it, I don't know, maybe this is to phi star F here. We then take the inverse image of phi star F. And this in general will not be a module over smooth functions. So we multiply with C infinity of M in the end. And somehow when the map is a surjective submersion, because T phi is fiberwise surjective, this gives us a nice, well-behaved notion, but in general, it doesn't. Okay. So the last few minutes I would like to spend on talking a little bit about what invariants we can associate to singular foliation. So what are the ways to distinguish them locally? How do they behave locally? And the main reason why we do have a decent, I don't know, invariant theory, or why we know that they behave well at all, is that even though we don't have one unique normal form from them, we still know that somehow in the vicinity of a leaf, they behave nicely. So And this is somehow lemma that we have a splitting near any point of a singular foliation f. We have a local diffeomorphism to some rk times rn minus k, so we can split into two groups of coordinates. But now the foliation will not just be the k directions are in the foliation and the n minus k aren't. It's going to be a little bit different. So it's going to be with the foliation generated by dx1 to dxk. So those are the direction of the leaf. And then some other vector fields, y1 to yn. So I use little x coordinates and y coordinates. And here, the yi, which in principle they are functions of x and y, they are just functions of y. So we don't depend on the leaf direction. And they all vanish at 0. So this means that locally, a foliation is always equivalent to more or less the product of a regular foliation with a foliation vanishing in the origin. This is very similar to theorems, splitting theorems, which exist, for example, in Poisson geometry, that you can always locally see a Poisson manifold as a symplectic manifold plus a Poisson structure vanishing at the origin, at least locally. Sorry, 1 second. Okay. So the proof of this splitting lemma heavily relies on the fact that we have a finite dimensional, the local finite dimensionality, and it uses the involutivity. And somehow, once one has this lemma, the fact that dynamical leaves and geometric leaves coincide becomes a corollary, and kind of a lot of the basic theory of singular foliation is somehow anchored in that statement. Okay, so now the first invariant we can associate to a foliation is called isotropy. And the idea is the following. Let us just look at the y part. Let us forget the x part. We know that locally we can kind of always split apart, and then we just restrict our attention here. And the fact that the foliation is locally finitely generated and involutive, so this now involutivity means that if we have yi and yj, the result has to be again in the foliation. So this will be some linear combination with some coefficients, which are functions, of the yk. And the idea of the isotropy Lie algebra of a singular foliation is to extract some functions from those coefficients, which already look like the things we would see as structure coefficients of a Lie algebra. Formally, we are going to work a little bit different. I'll write down the definition, which is directly visible to be intrinsic. So I'm at some point of the foliation of the manifold, and I define the isotropy in the point P as being, I take a vector field in the foliation, which vanishes at P. So this is somehow, this intersection is just to forget the x directions. And now I divide out any multiple of of a vector field in the foliation by a function vanishing in P. So IP, I called it MP earlier, I think, so I'll just write it. It's the functions with f of P is 0. And so this is a purely algebraic definition. Because the foliation is a locally finitely generated, this will be finite dimensional. Actually, its dimension will be somehow the lowest possible numbers of local generators we can take for the singular part. So it will be somehow the n if we picked y1 to yn minimal. And if we just write down the Lie bracket of vector fields, we can see that the denominator is an ideal, and that this will actually be a Lie algebra. So this Lie algebra, called isotropy Lie algebra, it's different for different foliations from the dynamical viewpoint, even if they are the same geometrically. So we can build all those foliations of vanishing in Rn to a certain order. And then the isotropy Lie algebra at the origin would always be some sort of symmetric algebra. And except for the case of k equal to 1, it will actually be an abelian one. So this is somehow a first way how we can measure our foliation at a point. It will give us different things. So for dynamically different foliations with the same leaves. And actually, because of this local triviality, the GPs, they lie next to each other very nicely. And if we somehow don't do this trick with vanishing in P, but if we localize along a leaf, we can put them together into a Lie algebroid. So there is a Lie algebroid, AL, for every leaf of a foliation. So it's a Lie algebroid over L, meaning its anchor goes to TL. And at every point, the kernel of it, so the things with trivial anchor, will just be the corresponding isotropies. So we can put on somehow the tangential information of dynamics along the leaf together with the isotropy information and get a Lie algebroid. If you want to look at it algebraically, we can also say that the sections of this algebroid is the same thing as f divided by ILF. And IL are now the functions which vanish along the leaf. And for this to be technically true, we have to pick a closed leaf. Otherwise, there is some small technical problem to be solved. So up to technicalities. And this is somehow one instance where this Serre-Swan theorem from earlier becomes useful. We could completely forget about these constructions where I would need to explain how do they fit together smoothly, the different isotropies, but we can write down this, check that it is a projective module, which is a consequence of it being a locally free module, which is a consequence of the local splitting lemma, which we had before. And then we already know that it will give us a Lie algebroid, or a vector bundle, and then the bracket will actually turn it into a Lie algebroid. Okay, do I understand correctly that I have around 5 minutes? Or what's the...
Yes, it's exactly the time when we should finish is 4 o'clock.
Okay. So maybe I would, maybe I would just like to say that this machinery using somehow this module language to define invariance of the foliation, it's relatively flexible. So for instance, if you say that this is somehow giving me the infinitesimal generators of the foliation, but I actually only care about the linearization. I want to linearize the foliation. Then I can very easily say that, okay, I'm taking the same foliation, but instead of just dividing out ILF, I'm also saying that I also identify everything which vanishes quadratically. So I write down IL square of xm. Of course, it has to be a part of the numerator, so I can do it. And again, I verify this is projective. This is comes from a vector bundle, and I could call this vector bundle AL-lin. And it somehow from a direct calculation shows you this is actually again a Lie algebroid, and we have somehow a natural map from AL to AL-lin. And this AL-lin, it's relevant because if it is semi-simple, then we can do, in some sense, linearize a part of the foliation. So this might be the theorem I would like to end with. If L is simply connected, and AL-lin semi-simple, and when I say semi-simple, I mean that its isotropies are, so the individual kernels of the anchor are semi-simple Lie algebras. Then there exists a section of the projection from the foliation to AL-lin. And this somehow means that we have a Lie algebroid acting on our manifold, generating a part of the foliation. And I'll finish with two disclaimers and an open problem. So technically, I should write there is a little bit of technicalities to actually make this precise. And the second disclaimer is that the theorem which we have proven with Camille Laurent-Jangou is that there exists a formal section. The existence of one which actually converges is an open problem even for point leaves. And yeah, so far I think there are very little, the very few cases where one can actually give an argument why the formal thing can be turned into a convergent one, which would be somehow an actual action, not just one on the level of infinity jets. And maybe I would like to note that the simply connected condition, it is necessary for the argument with somehow this linearization. Normal forms of foliations near leaves, which are not simply connected, were recently proven also in this formal category by Camille Laurent-Jangou and Simon Fisher. And yeah, getting convergence in any setting is wildly open. I think I'll stop on that. Thank you very much for your attention.
Thank you very much for a very interesting talk. We have like 2 or 3 minutes for questions or comments. There were questions during the talk, but maybe somebody wants to add something.
Yeah, so I have a question, might turn out very naive, but if you consider surjective submersions and in particular principal bundles, you have a theory of descent of structures over the total spaces of those guys, such as bundles, gerbs, whatever, to the bases. Meaning you can answer the question when a structure on the total space is a pullback by the surjective submersion of a similar structure on the base. You're constructing a simplicial object over the nerve of the surjective submersion, and then you know that this is the case. Is there anything you can sort of say about that in this very general framework that you painted? The reason why I'm asking, that's a remark for younger colleagues, is for our students, is that one would be tempted to think of the foliation as a decomposition of, say, a configuration space, or the fiber of the configuration bundle of a field theory or whatnot, into symmetry orbits, let's say, and then one would like to gauge this symmetry. So hence my question.
So if the vertical vector fields are part of your foliations, then I think that then it is the pullback of a foliation on the quotient. At least locally, this is true. I would not expect a problem globally. I think it's somehow, to a certain extent, again, a consequence of the splitting theorem, that we know that submersions are basically locally projections, and if the fiber directions are inside the foliation, then in the splitting theorem, you're basically projecting only leaf directions. So there, I would expect it to hold. If the fiber directions are not in the foliation, then I think there is very little. Then it cannot be a pullback, because the pullback would always have the fiber directions. So yeah. So I think that M to N submersion, let's say surjective, F in XM is the pullback of F prime on N if and only if gamma of kernel of T phi is an F.
So my question was somehow motivated by the appearance of the Lie algebroid here in your picture, which, if it were to integrate to a Lie groupoid, could probably be gauged the way we sort of proposed recently with Thomas Strobel, by variant of the principal bundle construction. So by a variant of the Cartan-Borel construction for the Lie groupoid. That was somehow something that motivated my question, the appearance of this Lie algebroid, which could integrate, right?
Mm-hmm. So this Lie algebroid, maybe I should say, so it is a Lie algebroid only leaf by leaf.
Mm-hmm.
So I'm currently working with Alfonso Garmendia, where we try to understand somehow a sort of smooth diffeological object which unites all of these algebroids together. And then the holonomy groupoid or the fundamental groupoid of the foliation are integrations of them. This is all happening in a world which is a little bit worse than smooth manifolds. So you have to go to diffeological spaces, but among diffeological spaces, those are extremely nice ones. They are all somehow behaving a little bit like a fibration with smooth fibers and a smooth base. It's just that the dimension of the fibers is allowed to jump. In general, so if you have some sort of nerve construction in this setting, and you don't only need it along a leaf, but you need it globally, then I think it's relatively complicated, because those objects, which are a little bit generalized, they behave relatively badly when you do fiber products along them. So this is somehow the biggest problem in this setting. There is somehow more generally for diffeology, there is a work of Christian Blomann on trying to define somehow reasonable tangent bundles for them and work with those tangent bundles. And the main difficulty why this theory is getting somehow quite complicated is trying to do fiber products, to my perception. And I think the same problem could occur here. But yeah, So
Back with
I don't know
projective
exactly.
submersions as a nice category, so to speak. Yeah, again, right. We'll see. Okay,
Mhm.
thanks.
Any other comments or questions?
Yes, in the real analytic category, singular foliations always exist. I mean, for Lie algebra actions, that means for involutive uh, distributions of non-constant rank. Does real analyticity simplifies also other parts of your work, like the second part of your talk?
So you're saying that in the real analytic category, you don't need the condition of locally finitely generated. It's automatic because
Yeah,
analytic functions are a Noetherian ring.
that's what I'm
Um,
saying. Yeah.
mhm. So yes, certain things become simpler, but not not much simpler. So I think that this theorem about um, getting a map back from the isotropy into the foliation. So if we kind of just assume point leaves, this would be the case. I think this is even for in the real analytic category or in the holomorphic category, not known. I think certain things about this linearized holonomy Lie algebroid become a little bit simpler because you know that the semi-simple part is in the linear part. You know that this is somehow nilpotent, this the fiber of the map from AL to the linearized one. So this one. So it does help at certain points. I think if you're interested in somehow a higher structure perspective, there is this idea of DG manifolds lying behind foliations, which for a general singular foliation might not be true. At least there might be no finite dimensional one. And when you're in the real analytic category, or even if your foliation locally is real analytic, those will always exist. Also, you will know that all your regular leaves are of the same dimension for something with real analytic generators, which might not be true in general. So there are some examples of a foliation which is somehow just point, 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 and then a half line. And such things cannot happen real analytically.
Yeah. Okay, thank you.
Okay, so since the time is up, I think that we should stop for now. So I'm stopping the recording.